Have you ever looked at a complex mass spectrum and felt like you were staring at a finished gourmet meal but had absolutely no idea what the recipe was? You see the final peak, but the ingredients, the structural secrets, remain hidden. Today we're stepping out of the snapshot world of Orbitraps or time of flight and into the ion kitchen. By the end of this 7-minute session, you will understand how to park ions in an electric field, chop them into pieces, and serve them to a detector. We'll master the components of the trap, the physics of the potential well, and the magic of resonance excitation. This is the foundation of structural proteomics and metabolomics. Welcome to the art of MS to the N. Before we cook, we need to know our hardware. Think of the ion trap as our pot. In a standard 3D quadrupole ion trap, we have a central ring electrode and 2 end cap electrodes. When we apply an RF voltage, V, to that ring, we create a dynamic cage. Now, for those of you using modern systems, you likely use the linear ion trap, or LIT. It's like an elongated pot that can hold significantly more ingredients, more ions, without them clumping together too much. Whether it is 2D or 3D, the principle is the same. We are using alternating electric fields to defy gravity and keep our molecules suspended in midair. Physics tells us that we cannot trap a charged particle with static fields alone. It will just slide away like a marble on a flat plate. But if we oscillate the field rapidly, we create what we call a pseudo-potential well. Think of a ball on a table that is flipping up and down. If it flips fast enough, the ball stays centered, because it never has time to fall off. This time-averaged effect acts like a physical bowl. The depth of this bowl, how deep our pot is defined by the average d sub xy, which equals V times Q sub xy divided by 4. The higher the voltage V and the specific parameter Q, the harder it is for your ions to spill out. This is exactly how we park our ions for analysis. Now, I know these formulas look intimidating, but here is the secret. They are just the boundaries of the pot. The Mathieu equation tells us if an ion's trajectory is bounded, meaning trapped, or unbounded, meaning lost. We look at 2 coordinates, a sub u, which equals -8 times e times u, divided by m times r naught squared times omega squared. This is related to our DC voltage. Then we have q sub u, which equals 4 times e times v, divided by m times r naught squared times omega squared. This is related to our RF voltage. If your ion falls within the stability zone, where beta sub u is between 0 and 1, it stays in the kitchen. If it moves outside, specifically past the limit where Q sub z equals 0.908, it gets ejected. Think of the stability diagram as the physical edge of your stovetop. Move too far left or right, and your ingredients fall onto the floor. Every ion in the trap isn't just sitting still, it is dancing. This dance has a specific rhythm called the secular frequency, or omega sub u. The formula for this is omega sub u comma dash n equals the quantity n plus 1/2 beta sub u multiplied by omega. This is crucial, because every molecule has a different mass-to-charge ratio, or m over z. Every molecule has a different natural dance move. Heavier ions move slower, lighter ions move faster. If we know the frequency, we can talk to specific molecules while ignoring the rest. This is the absolute foundation for everything from isolation to fragmentation. By matching the frequency, we can select exactly which ingredient we want to work with. Now we're cooking. In MS to the N, we want to break a specific precursor ion to see its fragments. We do this through resonance excitation. Think of it like pushing a child on a swing. If you push at the exact right frequency, the secular frequency we just discussed, the swing goes higher and higher. We apply a small supplemental AC voltage that matches our ion's rhythm. The ion gets excited, begins to swing wildly, and slams into background helium gas atoms. This is collision-induced dissociation, or CID. Pop, it fragments. We have just chopped our molecule inside the trap to see what it is made of, all without losing the other pieces. After we have chopped our ions into pieces, it is time to serve them to the detector. We do this through mass-selective ejection. By rampantly increasing the RF voltage, V, we move ions along the Q-axis of our stability diagram. One by one, starting from the lightest and moving to the heaviest. They hit the instability limit of 0.908 and are thrown out of the trap into the detector. The mass scale is roughly m over -z equals 0.0890 times V. It is like a perfectly timed conveyor belt, serving your data in a neat linear mass scale so the computer can record the spectrum. But wait, even the best chefs have limits. What happens if you put too many ingredients in the pot? This is the space charge effect. Because ions are all positively charged, they repel each other. If you have too many ions in your trap, they push each other around, distorting the very electric field we are using to measure them. This distorts the potential well we discussed earlier. The result? Mass shifts, where your peaks show up in the wrong place, and peak broadening, where everything looks fuzzy. As a practitioner, your job is to find the sweet spot. Enough ions for a strong signal, but not so many that the kitchen becomes chaotic and the data becomes unreliable. If you see your peaks getting broad or shifting to the right, do not panic. It is often just the physics of the trap. Heavier ions take longer to eject, which can create a calibration lag, especially under high-density conditions. Calibration is key here. You must use internal standards for high-resolution matching to ensure your oven is accurate. Now, ask yourself, is my mass accuracy off because of the machine's hardware, or because I overfilled the pot? If you can answer that, you have moved from being a simple button pusher to being a true mass spectrometry chef. We have covered a lot of ground today, from the Mathieu equation to the space charge mess. Remember this golden sentence: the ion trap is not just a filter, it is a laboratory. You now have the power to park, chop, and serve molecules with atomic precision. I will see you in the next lab.